This next chapter then is chapter 8, which deals with rotational motion. And so first off, for this chapter, we go back in terms of how we measure angles and angle measurement. And so you think in terms of an XY system, in terms of degrees, you get this as 0, 90, 180, 270, and then this would be 360 degrees. Now, in terms of this chapter then, however, we need to be talking about angles, but in terms of radian measurement. And so 0 degrees is 0 radians. 180 degrees would be pi radians. So you have that 0 degrees is 0 radians, 180 degrees is pi radians, and so then 90 degrees would be half a pi, which we write as pi over 2. Well, 0 degrees is 0 radians, 180 degrees is pi radians, and so 360 degrees ends up being 2 pi radians. Well, 180 is pi, 360 is 2 pi, so then 270 would be 1.5 pi, and we write that as 3 pi over 2. So you have then that one revolution, so all the way around a circle, would be equal to 360 degrees, which would be equal to 2 pi radians. Well, then, given an angle in degrees, you should be able to convert it into the corresponding angle in radians. So you get something like this. Convert 210 degrees into radians. And so we have our conversion factor is 180 degrees is pi radians. So 210 degrees would be it. And that is a proportion, and the way we solve a proportion is to cross and multiply and divide. So x would be 210 times pi divided by 180, and this becomes 7 pi over 6, and that would be in radians. Okay? So angles in this chapter will be in terms of radian measurements. Well, in chapter 2, we talked about linear velocity, which was the change in distance divided by the change in time. So chapter 2, we had linear velocity. So v was equal to the change in x over the change in time. And we said the units of this were in meters per second. Well, now in chapter 8, we get the corresponding thing here in terms of angular velocity. And so we get, this is going to now be the change in theta over the change in time. Theta will be in radians. Time is in seconds. And so omega will be in radians per second for our angular velocity. Right? Well, there is an equation that relates linear velocity to angular velocity, and that equation is that v is equal to r times omega. Okay. So this is the linear velocity, which will be in meters per second. R would be the radius, which will be in meters. And then this is the angular velocity, which will be in radians per second. We can also look in terms of, we have from the earlier chapter in terms of rotational acceleration, so what we call A sub r. And so rotational acceleration, we said from before that A sub r was equal to v squared over r. But then we just saw here that v was equal to r times the angular velocity. And so A sub r would now be r times the angular velocity, that quantity squared, divided by r. Okay? And so if I do this, we get A sub r would then, first off, would give me r squared times the angular velocity squared divided by r, but then this simplifies to this. Okay? And this velocity, or this acceleration, is the centripetal acceleration. We can also look in terms of the angular acceleration. So we said from chapter 2 that linear acceleration was just change in velocity over change in time. And so now we get angular acceleration is going to be the change in angular velocity over the change in time. So this will be W, or omega minus omega naught, divided by the change in time. And we said in chapter 2, acceleration was in terms of meters per second squared. And so now here, this will be in terms of radians per second squared. So we have in terms of angular acceleration. Well, in terms of an object going around, we can look in terms of its frequency and the period for that object. And so frequency, then, is the number of complete cycles per second. And so frequency is given by the angular velocity divided by 2 pi. 2 pi represents going all the way around. And frequency, this quantity, is measured in terms of hertz. Which means that, of course, that the angular velocity is going to be the frequency times 2 pi. And so we can rewrite that and make it look better. And so we'll just rearrange this a little bit. And so we get 2 pi times that. And we get it. Right? And then period, then, is the time frame to complete one cycle. And so period will be measured in terms of seconds. And the relationship between period and frequency is that they are reciprocals of each other. And so this is the symbol for period, and it will be measured in seconds. So then in terms of rotational motion and those quantities, we can look at those equations we had in chapter 2 can now be rewritten in terms of these quantities from chapter 8. So, you had the equations from chapter 2. Okay. and the quantities involved in that. And so in chapter 2, we said we had x, which was distance. We had v, which was velocity. We had a, which was acceleration. And then we had t, which was time. And so we have these equations: v equals v naught plus at, x equals x naught plus v naught t plus 1/2 at squared. V squared equals v naught squared 2a delta x, and v bar, which is average velocity, was v plus v naught over 2. And those were what we had from chapter 2. Well, then you get to what those look like in terms of chapter 8. And so from chapter 8 then, instead of distance, we now have theta, which is going to be the angle. Instead of velocity, we have omega, which is going to be the linear, or the angular velocity, the angular velocity. We have alpha, which is the angular acceleration. And then we have t, which is still going to be time, which will be in seconds. So all these equations we have here can now be rewritten in terms of their counterparts from chapter 8. And so instead of v equals v naught plus at, we now get omega naught alpha t, and then this will be theta, initial theta, omega naught t, 1/2 alpha t squared, and then theta squared, that squared, 2 alpha, change in theta, and then average will be given by that. So all those equations from chapter 2 can be rewritten in terms of their counterpart from chapter 8. So now let's look in terms of a problem that makes use of those equations and how we go about solving them. And so we get a question that is something like this. So you got that a fan is turned off when it is running. So when it is turning at a rate of 850 revolutions per minute. And then, if it turns 1,500 revolutions before it stops, there are two things we can possibly say. First, A is
I'm so sorry, I didn't know you were filming.
what was the angular momentum? And part B, how long does it take to come to a stop? So we're going to find those two things. So first off, we need to look at our numbers. So we know that it's first going at 850 revolutions per minute, okay? and that is my initial 850 revolutions per minute. But we want that to be in radians per second, so we need to multiply that by the corresponding conversion factor. And that'll give us 89 radians per second. It goes through an angle of 1500 revolutions. Okay, so theta is 1500 revolutions. But we need to multiply that by the conversion factor, which is that 1 revolution is 2 pi. So we multiply that by 2 pi. And that'll give us 9,425 radians is the change in theta. So now we can answer our 2 questions. And so for part A, we're going to have that. We're going to use this one. We've used this before in terms of like chapter 2. We've used this a few times where b squared equals v naught squared plus 2a delta x. So now we want to take this equation and we're going to solve for this. And we've done that before. And we get that this will be given by this. And we've done this before in terms of chapter 2. So now we can take our numbers and we can plug this in. We know that it's coming to a stop, so the final angular velocity is 0. So we're going to get a minus, and this will be 89 squared over 2 times 94.25. And that gives us a negative 0.42 radians per second squared. And so that would be the acceleration on our system. The second part then was how long does it take to come to a stop? And so for that, we can use this equation for part B. And we're going to solve this for t, and so we get that t will be given by this. And so again, the final angular velocity was 0, and so this will be, that t will be at minus 89 divided by the negative 0.42, and this will come out to be that the time frame to stop will be 212 seconds for this thing to come to a stop. So we have in terms of using those equations that deal with rotational motion and in terms of my object. Well, I think in terms of rotational motion is this idea of torque. So if you think in terms of using a wrench to loosen a bolt. And so, for example, we have our bolt, and we have our wrench, and something like that. Okay? And we want to apply some torque. So we got a choice. Do we want to push here at A, or do we want to push here at B? Okay? So if you think about it, you want to get the most out of what you're doing, then you really want to be as far out on the wrench as you can when I push, if I want to do anything with this bolt. And so we get that torque is given by RF sine of theta. So this is our symbol for torque. Okay? And so you got that torque will be measured in terms of a meter Newton. R is your distance, really how far you are from that turning point, the pivot point, which will be in meters. F is force, which will be in newtons. And that depends on the angle. Well, if I'm doing this where this is truly perpendicular, then you got that the sine of 90 and the sine of 90 is 1. And so we just get that torque is going to be given by R times F. Right? But then if I'm applying where I can't be at a 90-degree angle, so now I have to do something like this, then we have to know what this theta is in there. Okay? So you get something like this. So what would be the torque? On a wrench, if R is equal to 25 centimeters and theta is 70 degrees when a 30 Newton force is applied. Okay. So the torque then, 25 centimeters needs to be converted to meters, so 0.25 times 30 times the sine of 70. And so this comes out to be 7.05 newtons. And that would be the torque on my wrench. Well, in terms of an object that is rotating, we can look in terms of the dynamics in that system. So rotational dynamics. And you get that the torque, the sum of the torque on the system is given by I times the angular acceleration, and this is the moment of inertia, which is dependent upon the shape of the object and what is the axis of rotation. And in your book there is a table that gives the moment of inertia for various shapes, and you will also find it in the notes. So in terms of rotational kinetic energy, we get that the kinetic energy rotation will be given by 1/2 the moment of inertia times the angular velocity squared. The total kinetic energy then of my system is, you get the kinetic energy total would be the linear kinetic energy, so kinetic energy linear, plus the kinetic energy due to rotation. So this would be 1/2 mv squared plus 1/2 the moment of inertia times the angular velocity squared. So if you think in terms of a tire going down the road, it has both linear velocity and it has rotational velocity. Okay? And so we'll go through an example in terms of how this works for a particular problem. So we'll look at this problem on dealing with this whole idea of finding the total kinetic energy for a system. And so you get this question: what is the total kinetic energy for a thin hoop with a mass of 3 kilograms and a radius of 12 centimeters, rotating about its center if it has a linear velocity of 5 meters per second. So we want to find the total kinetic energy here. So we know the mass is 3 kilograms. We know R is 12 centimeters, but that needs to be converted to meters. And so we get that. We know the linear velocity is 5 meters per second. And we want to find the kinetic energy total. Well, kinetic energy total, we just said, is given by 1/2 mv squared plus 1/2 the moment of inertia times angular velocity squared. Okay? Well, we know m and v. We don't know what I and angular velocity is yet. So first off, I. I is again in the table, and you'll find it in the notes, also it's in the book. But I for a hoop is given by mr squared. And then we have, from the equation we saw earlier, given that we know the velocity, we know the radius, we can find the angular velocity. So we have this equation earlier, that v was equal to r times angular velocity. So the angular velocity is given by v divided by r. And so we would have that this would be 5 divided by 0.12, and we get 41.7 radians per second. So we know that. So now we can take all this and let's rewrite this in here. So we get kinetic energy total is going to equal 1/2 mv squared plus 1/2 mr squared angular velocity squared. So now if I take and I plug in all my numbers, we get 1/2, this is going to be 3 times 5 squared plus 1/2 the mass, which was 3, the radius, which was 0.12 squared, times my velocity, angular velocity, which was 41.7, and that number squared. Okay. And we plug all that in, we end up at 75.1, and that'll be in joules. Okay. So we get in terms of the angular velocity on or the total kinetic energy. So this part is the linear kinetic energy. This part would be the rotational kinetic energy. Right? Well, in terms of an object that is spinning around, we can also look in terms of its angular momentum. So we had in the other chapter in terms of linear momentum. This chapter you now get in terms of angular momentum. And so angular momentum, and the symbol for that is L, is given by the moment of inertia times the angular velocity. So this is the angular momentum. Which will be in terms of a kilogram meter squared per second. I is moment of inertia. Again, that is dependent upon the object. And then this is the angular velocity. So this is in terms of kilograms meters squared, and this would be in terms of radians per second. Okay. So angular momentum. So what are ways you see that? If you think in terms of a diver, in terms of diving from the 10-meter mark or something, and they spin, basically you got that in order to go faster, they tuck themselves in, and when they want to slow down, they spread out And you get that there would be a conservation of angular momentum. Momentum before is going to equal momentum after. And so a question dealing with this is you get what is the angular momentum of a disk rotating about its center if the mass is 2.5 kilograms, the radius is 75 centimeters, and it has an angular velocity of 3.2 radians per second. So the momentum is going to be given by this. But we have, first off, that this is a disk, and so the moment of inertia is given by 1/2 mr squared. And so the angular momentum will be given by 1/2 mr squared times the angular velocity. Okay? So we know the mass is 2.5 kilograms. We know that R is 75 centimeters, but that has to be converted to meters. So 0.75. My angular velocity is in the right units. And so now we can take our numbers and we plug them in here. So I get 1/2 times 2.5 times 0.75 squared times 3.2. And we end up at 2.25 kilograms meters squared per second. And that would be the angular momentum on our system. And with that, that will conclude Chapter 8.